Okay, here we have another solids of revolution example. And in this, we would consider the problem of the region bounded by the line y equals x and the parabola y equals 1/3 x squared is revolved about the line y equals 5. And we want to find the integral that can be used to compute the volume of the resulting solid. Here we have an illustration of the problem. Our region is bounded on the left by the line y equals x and on the right by y equals 1/3 x squared. And these two curves intersect at the origin and at the point 3, 3. And then we're going to revolve this about the line y equals 5. So we have our outer paraboloid and inner thing, we have a cone here. So we can approximate this volume using washers, and if I have 4 washers, I'll get a crude approximation adding up the volume of these 4 washers. If we use more washers, we get a better approximation. So here's an illustration where we have 14 washers. That's one view of it. You can have a side view here. And we can have the view from a little bit behind the object. So here's a cross section. And here's our illustration of a single washer. So the ith washer, the subscript just refers to the number that washer is. So I here go at 1 for the first washer and go up to the 14th washer will be I equals 14. And so this thing, we have a inner radius here from the line y equals 5 to the line segment, and we have an outer radius if we go all the way down here to the paraboloid, or parabola, I should say. So here's my inner radius and that outer radius. I have a thickness change in x. So we can find the volume of this washer. It's just going to be the cross-section area times the thickness. But what is this cross-sectional area? The cross-sectional area is just difference in the areas between the outer circle and the inner circle. So I have pi capital of r sub I squared minus pi little of r sub I squared, that quantity times change in x. For the outer radius, I might notice that I'm going down here to this parabola, right? So I'm going from the center all the way down here to this parabola, and I have a little y sub I right here, and I might notice that those two guys add up to be 5. Now, I want this r sub I in terms of x sub I, not y sub I. So I subtract my y sub I from both sides, get capital R sub I is 5 minus y sub I, but because we're on this parabola y equals 1/3 x squared, our y sub I is 1/3 x sub I squared. And so this is our outer radius right here. We're going to use this in a little bit. And now we consider the inner radius. So the inner radius, we're going from the line y equals 5 down to this line segment. And our inner radius is just that distance. And then we have our x sub I, y sub I. Right? And again, we might notice that r sub I plus y sub I is 5. Right? Just you can see that graphically here. So my little r sub I is 5 minus y sub I, which means that little r sub I is 5 minus x sub I because we're on the line y equals x. And so this is our inner radius. So now we know both our outer radius and our inner radius. So our volume was this cross-sectional area times the thickness, but I know the cap of r spine, I know the little r spine, just substitute those in there. So if we add up these n washers here, we'll get an approximation to the actual volume. So for us, we had n was 14. We can write this in sigma notation, just the sum equals 1 to n. And I just have that expression again. Now, if we let n go to infinity, if we take more and more of these washers, and our thickness is going to 0, and the limit of these Riemann sums, we get this definite integral here. You might notice that the x sub I is replaced by x, and the change in x corresponds to the differential. And if we like, we can evaluate this. It's not difficult. You just multiply these things out, use the power rule and the fundamental theorem of calculus. And that's that. Thank you.